Hey everyone, how goes it? And welcome back to Computer Science 146. Today, we're going to go over more programming review. More specifically, we're going to go into code organization today. In a previous lecture, we established that Java has a very specific structure that code needs to be organized with. This is no different from other programming languages. Java always assumes that functional code has to be inside of what's called a method, which is inside of another structure called a class, and those are grouped together inside of a project. What we're going to do is take a more specific look at each one of these parts. Let's start out with methods. Methods are a structure that basically groups together callable functionality. You can think of methods as basically being a verb. Those are the action parts of this programming language. Now, it's a good programming practice to create methods based on singular verbs. So, if you are speaking out loud and you notice using conjunctions, then it might indicate that maybe the verbs that you're using could be two different methods. Now, methods can either be static or dynamic, and for argument's sake, we're only going to refer to dynamic methods for right now. As mentioned before, methods in Java must be within a class. This isn't true for other programming languages, but it is true for Java. It's good to know the structure of any programming language before you use it. Now, the syntax for creating these dynamic methods, which again are inside of classes, you start out with what's called a scope, follow that up with a return type, follow that up with an identifier, parenthesis, and then within those parentheses you have a number of parameters. What I just described is referred to as the method definition. From there, the functional code is grouped together in the body of the method, which is denoted by an open and closed curly brace. An example of a particularly useful method would be this one below. Public boolean is valid, passing in an int index. What this does is return whether or not an index is valid for some given array. So we know with arrays, it starts with the index 0 and ends at the length -1. This compound Boolean expression determines if that index is valid for that given array A. Looking more specifically in each one of the parts of defining a method, first let's take a look at the scope and its return type. The scope indicates where the method can be called from. Now there's two major types of scope that we're going to be using throughout this class. One is called public and the other is called private. A public scope means that you can call that method. That method can be accessed outside of that class. A private method can only be called internally within the class. This is really great for creating specific kinds of methods that are considered helper methods. It just basically helps out other methods that are internal to this class. Following the scope, we have the return type, and this allows a method to pass back values. Any type can be a return type, but there's a very special kind called void, which indicates that the method returns no values. Now, if the return type is anything but void, then you must return that value within the method, and we use the reserved word return in order to return said value. Also keep in mind, return immediately stops the method. It immediately exits the method with that value. And a very common syntax error that can come up from this is that every path within a method must return one of those values. Looking at the example below, we have public double feet to inches and a parameter double feet. Now if you notice, the return value is not null, it's double. And what we're returning here is both 0 or this number of feet times 12. Now reading a little further into this method, if the feet here is less than 0, then we just return 0, which would indicate that any foot amount that is negative might be invalid, so we just return that value. Otherwise, we return this feet times 12, in other words, getting the feet into inches. In either case, you could see that if this is true, we return a value, and otherwise, we return that value. So in fact, all of the paths in this program return some sort of value, which is a double. Anything that is not the void type has to return a value. The next part, After the scope and the return type, you have the identifier and the parameters for a method. The identifiers give a name to a method, and it's the same rules for a variable. Variables give you a way that you can access and store information. Identifiers for a method allow programmers to call those methods. In other words, to use those verbs. Now, just like the rules for variables, it's good common programming practice to camel case the identifiers for a method. It's also really good practice if you assume that methods are basically verbs, give them verb-like names. Make them have an action. Now, after the identifier, we have a set of parentheses. And within the parentheses, those are what's called parameter values. Parameter values act as variables for information being passed into the method from some sort of outside source. The scope of these variables, these parameters, only exist within the body of the method, which is very similar to what we've seen before. A variable only exists within the body of which it was declared. So if you declare a variable inside of an if statement, that variable only exists inside that if statement. Similar here. These parameters are defined for the method body, but anything outside of that, you cannot access that information. For every one of the parameters that we need to pass to this method, you have to declare it, which involves using the type followed by an identifier. And if you have multiple parameters that need to be passed inside of a method, they should be separated using a comma. Now if we look at this example, what we have here is something that determines the max value given a value 1 and a value 2. Now if value 1 is greater than or equal to value 2, then we just return value 1. Otherwise, we return value 2. Keep in mind, always think about the verb and the information that you need in order to use that verb. This usually indicates that we may need parameters, so pay very close attention to when you hear things like is given or is provided, because that might be a parameter or a method. Now, calling a method depends on where you're calling it from. If you're calling a method from inside the class from which it was defined, all you need to do is use the method's identifier followed by its parameters. In other words, the parenthesis. Now, whenever we are referring to these methods, again, we are assuming these are dynamically created methods. And for those methods, if we are referring to one to the other, it's a good idea to use the reserved word this. Now, if we had to call a method from outside the class where it was defined, one of the first things that we need is we need an instance of that class. An instance of a class is referred to as an object, and this object has to be constructed. If you were to try to call a method, an action, from an object that does not exist, this is a very specific kind of error called a null pointer exception. Now, assuming that we do have a constructed object, the way that you call a method from that object is using the dot followed by the identifier of the method and its parameters. Whenever a method is called, the information in memory is pushed onto this thing called a call stack. Taking a look at this example here, we have public int getValue from array given an int index. Now notice that it calls isValid. Now that was a method that we defined a little bit earlier that returned true or false, indicating if this array's index was valid. Now if this is not valid, then we return -1. But if this is valid, then we return the value that is found at this index. This is an instance of a method calling another method that is assumed to be defined internally within a class. Now, in order to go in more detail, let's see how this works inside of memory. Now, as you can see over here, we have this thing called the call stack, and the first thing that's in this call stack is called the main method. This is the entry point for our program that is calling the rest of these different methods. Now, what we're going to assume here is to the left, we have two methods that are defined. And get value from array. This is called from the main method. So if we start right here, this is being called from the main method. And as soon as we get to this point, what happens in memory is the information regarding this method is created here, and then it is pushed on top of the main method. So we, in essence, jump to this code and run it until it's complete. Now, going internally here, we're going to pass the int index, which is 2, as we can see in this parameter right here, and we're going to then check if it's valid. Now, we get to this part. So if not this is valid given this index, this is calling another method, which means we are going to jump from this point right here down to that part there, while still keeping track of where we left off. Now, once we do that, we are then going to push the instance of isValid on top. Notice that we assumed that int index was 2. And remember, this is a variable value. So from the main method, we passed get value from array with the value 2, so 2 was stored inside of index. This was then passed to this variable right here, int index, and now we're going to run this code. Now, once we enter this method, we are going to assume that index 2 is valid. So this compound Boolean expression yields a true value. We then return that value back from where we came from. Now, once we do that, isValid has completed. This method is done. Whenever a method has finished running, we simply remove it from the call stack, or in other words, we pop it off the call stack. Now we resume where we left off. And what we have here is valid return true, not true is false. That means we jump down to here and we return the value found at this index given the array A. And now this is returned, this method has completed, and so it is finally popped off the call stack, and that value is returned. That's how method calling basically works in memory. You can always remember this as a last in, first out structure. Now, the other part that we haven't mentioned yet is methods can be static. Now, these are unlike dynamically created methods because these are created once in memory only. These do not require an instance of an object in order to be called. This is why sometimes they are called class methods. This is an excellent technique in order to create functionality that does not depend on the instance of a class called an object. And in essence, this shares functionality across not just one instance, but across every instance of this class. Now, as these are statically defined in memory, and they are not dynamically created, you cannot use the reserved word this. Another thing to keep in mind, static methods can call other static methods. Dynamic methods can call static methods. However, a static method cannot call a dynamic method. Dynamic methods require an instance called an object. However, statically defined methods do not use objects. Now, using methods is the first means in order to organize code, grouping it together in functionality and really considering what your verbs are. To go further with this, we introduce this concept called object-oriented programming. The idea behind this is we use these things called objects in order to better organize our code. Some of the key concepts in object-oriented programming include encapsulation, inheritance, and polymorphism, which will be discussed in a little bit. The cornerstone of using object-oriented programming is using this structure called a class. A class groups together data with the functionality. And you can think about classes in this way. They are used to create nouns. They are the ones that create the instances that we call objects. So once again, classes create these nouns, grouping together information about the object along with the functionality. There is a difference between a class and an object. An object is an instance of a class. A class only defines what methods and what properties can be replicated into the structure called an object. Classes become types. It becomes types that programmers actually define themselves. Now, in some of my previous courses, I've gone over the 7 steps to creating and using a class. The first step is define the class. Next, declare the instance variables, make their scope private. 3, constructors, 1 default, 1 parameterized constructor. 4, accessors for every instance variable. 5, mutators for every instance variable. Check for those valid values. 6, some other useful methods, toString and dot equals are nice. And finally, use the class itself. Now, these are just good rules to follow to get started, but there are going to be some cases where we have to make decisions about whether or not we're going to include certain parts of this. Before we get to those trade-offs, let's just take a look at each one of these steps one by one. That way we can create a class. First, we need to define the class. Once again, the identifier becomes a type. And the class's identifier has to match the same rules that we found with variables and the same rules that we found with methods, with one slight change. Classes in Java, it's good programming practice to always uppercase the first letter, unlike with variables and unlike with methods. As we consider classes to create these nouns, it is a good idea to create noun-like names for these classes. In Java, it is required that the class's name, its identifier, has to match the file name. If you don't have this, this is automatically a syntax error. Now, the scope of a class is usually defined as public, but there are some cases that we'll get to later on in this course where it may not make sense to make a class public. The syntax for creating a class is simply you have a scope, usually public, followed by the reserved word class, and then the class's identifier. From there, within the curly braces, that is the body of the class where we are going to put properties and also methods. Next, we create the instance variables. These are the properties of a class. You can think about this as the data portion of the class, and the properties are used to describe a specific instance of that class. In other words, the properties describe a certain object that is of that class. It is really good programming practice to go ahead and assume that the scope of instance variables should be private. We do this because of one of the first principles of object-oriented programming called encapsulation. This simply means information hiding. We only want information accessible if we deem it necessary. So in our example, as we can see in the previous one, we already defined this public class person. Now we have the 2 instance variables called name and favorite number, both of which their scope is private. Next, constructors. Constructors are used to construct an instance of a class, an object, in memory. Constructors allow us to replicate the code found inside the class. Using this reserved word new before a constructor, what this does is replicate. It copies all of the information that you've written in one class inside of memory. And in this way, we can have multiple instances of the same class, which we call objects. And every time we create a new instance of that, it replicates all of the code that we've written one time in a class over and over again. This is a common practice called dynamic allocation, and all of the properties and the methods that are found in the class are created for that unique instance. Constructors are a special kind of method which do not have a return type, And its identifier has to match the class's identifier. There's two different versions of constructors that are very common. One is called the default constructor, which basically sets all the properties, the instance variables, to some default valid value. There's also a parameterized constructor, which is very useful, and what this does is set all the properties to a given valid parameter values. A parameterized constructor has to error check, and in order to do this, it's a good idea to just call the mutators from it. Now, looking at the syntax for a constructor, you can see that it starts out with public, and then no return type, and the identifier has to match the class's identifier. Now, we can tell that this is a default constructor because it has no parameters inside the parenthesis. The purpose of a default constructor is to construct an instance of that object and also set its properties, the instance variables, to some kind of default value. Now, the syntax for a parameterized constructor follows the same formula. Public, no return type, and the identifier has to match the class's identifier. The big difference is the parameterized constructor has parameters that basically match each one of the instance variables. This gives us a means to both construct a new instance of an object and set its properties, if they're valid, at the same time. Looking at our running example, as you can see, we create a default constructor for this person. There's no parameters here, and we set this dot name to none yet, and this dot favorite number to 0. Now down here is the parameterized constructor, and as you can see right here, there's a comment that says call the mutators. We haven't discussed mutators yet, but what we would do is fill in this part right here, calling the mutators, thus checking each one of these values and setting it if it is valid. Next, we create accessors for every instance variable. Accessors are very special methods that give access to the properties outside of the class. We have to do this because we make the instance variables private. So in order to give access to these values outside of an instance, we create a special method to do this. It is a good idea to go ahead and create an accessor for every instance variable in a class. Accessors are methods, but they are very extremely formulaic methods. Basically, the main idea is you start out with public. Then, for whatever instance variable that you're returning, you have its return type match that variable's type. You then follow with the identifier, which is get, followed by the variable's identifier, no parameters, and then return this dot, whatever the instance variable's identifier is. So for our given example, we had two instance variables, name and favorite number. As we can see here, this is an accessor for the name. It starts out public string, because name is of type string, get, the identifier, which is name, and then we just return this dot, the instance variable, name. Same thing here with favorite number. Public int, the favorite number is an integer value. Get, here's the identifier, favorite number, and then we return this dot favorite number. After that, we create mutators. Mutators give us the ability to modify or mutate the value of an object's properties. The main goal of a mutator is this. We set those values only if the value we're trying to set it to is valid. Mutators are great for error checking those values of an object. It's also a very good idea to create mutators for every instance variable. Now, much like accessors, they are very formulaic. Now, in this case, the return type always has to be void. The method's identifier is basically set, followed by the variable's name. Mutators have to have a parameter value. What you're trying to do is set some value given this parameter's value. But you only do that if it is valid. It is good programming practice that if you're setting the value of an object type, so a non-primitive type, to go ahead and check whether or not the parameter that you're passing in even exists. Check if its memory address is not null. Applying this to our example, we have public void set name, then string a name. What we want to do is set the instance variable name to this if this is valid. Now, a string is an object type, which means it may not exist in memory. And the way that we check that is this way. If this parameter here, a name, is equal to null, null means it doesn't exist, and so what we do is set this to none yet, which was our default valid value. However, if this parameter, a name, is not null, then we set the property this.name to a name. Now we have another example here for the favorite number. But notice we're not doing any sort of error checking. This is because us as programmers, we have taken the stance that anyone can choose any number to be their favorite number. There is not an error here, so we're not going to check for it. Make sure that whenever you're writing a mutator, does the values that are being assigned to these properties make sense? And also, don't forget to call your mutators from your parameterized constructors. Now we get to other useful methods. These are basically the actions, the verbs that are very specific to this kind of object. Now, putting a lot of these aside, there are two very common methods that are particularly useful, and one is called toString, and the other one is called equals. The toString method returns a string value with all of the properties in that object concatenated together. This is very useful to use while debugging. The equals method verifies if the properties of one object is equal to another object's properties. The .equals method needs to be used for object types. Double equals for object types does not work the way you may think. Double equals for primitive types is the comparison operator, and it says, does the left-hand side equal the right-hand side? However, with objects, what it is referring to is not the contents of the object, but the memory address of the object. If you wanted to check for the contents, whether or not this object's properties are equal to another object's properties, then you need to use an equals method. Now over here is the general syntax that you can follow with toString and equals. ToString is always public string and toString, and then you just return all the properties concatenated together in a string. For equals, it starts out public boolean, so true or false, does this object equal some other instance of this object here? Now, as these are object types, the first check that we make is whether or not this other instance is null. If it is null, this instance doesn't exist, so no, this object does not equal this object. Now, if that is not true, then we check the values of each one of the instance variables. And always keeping in mind, if an instance variable is a primitive type, we use double equals. But if an instance is an object type, we use the method .equals, then we call the other instance's accessor to get that data. So with our running example, we have both the property name and favorite number. So when we create toString, we return the string name plus the property this.name. Then we concatenate that together with the string favorite number, and then concatenate that with the property this.favorite number. For the .equals method, we are comparing this person to another person, which we have named a person. So first check. Return a person is not equal to null. So has this person been constructed? Does this person exist? If that's true, then we move on, and we have to check this .name. Name is a string. This is a non-primitive type, so we need to use the method equals and then get this person's name to compare the two. Now, if that's true, we then check this .favorite number. This is a primitive type. It is an integer value. So this is why we use double equals to compare it to a person's favorite number that we got from its accessor. Now finally, after we have defined a class we now use the class. To use a class, we create an instance called an object by first declaring it. And this works just like we've described before with variables. You start out with the type, which in this case is the name of the class, followed by some identifier. Variables in Java assume default values, and the default value for an object is the memory address null. Simply declaring an object does not create the object. It only creates room for a reference. In this case, the reference is a memory address that points to the contents of the object. So in order to construct an instance, you have to use the word new followed by one of the class's constructors, and this should assign to the declared variable. This is the only way to create a new instance of an object. Simply assigning one object to another does not clone the object. All it does is have two different identifiers reference the same part of memory. Looking at the syntax, the declaration of this doesn't change from where we had it in variables. Now when we construct the new instance, we have the same identifier, the assignment operator, followed by the word new. New is then followed by the class's constructor. In our example, we have created an instance of person P1, or we've at least declared this, because right now P1 is still null. Now what we do is assign P1 and call the default constructor of person using this word new that creates a new instance of this type person and then saves the memory address inside of P1. Down here, we define another instance of a person, P2. We use new, followed by, this case, the parameterized constructor, which will set the name and the favorite number inside of this version of the person. By using the word new, we have replicated all the code that we have written inside of this class person. We don't need to copy and paste it. It does it for us. This allows code to be dynamically allocated. It allows code to be replicatable simply by using the word new. Going into a little more detail, when we refer to memory and objects, we have to remember that an object type is separated into two elements, a reference and the contents. The identifiers for objects only contain a memory address, the reference. Null is a very special kind of memory address that means that this object has not been constructed. We have not used the word new in order to dynamically allocate all of that code in this specific object. The assignment operator does not create instances of objects, only the word new does, and multiple identifiers can reference the exact same object in memory. The double equals checks the memory address and not the contents of the object, and as I've said before, you should use the dot equals method to compare the contents of one object versus another. You should only use double equals or not equals whenever you are referring to the memory address of the object, so you use those whenever you're referring to null. Inside of memory, if there has been an object that has been constructed, however, we lose the reference to that object, thus making it unreachable, that object is deleted. This is true for Java as it is a memory-managed language. It has a mechanism called a garbage collector that scans through memory, and if it discovers that there is a part of memory that is inaccessible to any other part, it simply deallocates it, removes it. We have an example to the side, but let's look at it in more detail inside of memory. So going through this example, let's see how memory and these objects work together. When we start out right here, we are declaring a new instance of this object, and we're calling it P1. Notice over in memory that the contents right now is null, and so this means that P1 has not been constructed. When we move to here, now what we're calling is the person's default constructor. This dynamically allocates, it creates the instance of that person. And as this creates the default constructor, as we can see here, person 1's name is set to none yet. And also person 1's favorite number is set to 0 because these were the default values that we set inside of that constructor. Now, what's assigned inside of P1 is just the memory address from where we start. So for argument's sake, we're just going to say that it points to memory address 44. And so this whole thing refers to the object, which we call P1. This is the contents of this object that we have just created, and it is referenced. It is pointed to by this identifier. This is the reference. This is the contents. Looking at another example, we first declare person P2 and its memory address is null. Now in this case, we use the parameterized constructor, and because this was not null, and this could be anything, you could see that each one of the properties were created and the values were assigned for this person P2. Once this is completed, once again, P2 refers to where this object is in memory. And again, we have the reference that is separate from its contents. Now we do the same for person P3, which is going to call the default constructor once again, setting the name to none yet, and the favorite number to 0, and it does the same thing where it basically points to there. Now going further with this, what we have done is we've created this Boolean B. Now we haven't created this in memory just because we're running out of room, but what we're doing here is using the comparison operator, the double equals, to compare P1 is equal to P3. Now remember, the comparison operator only looks at what is stored in the identifier. So in this case, what it's looking at is the value of P1, is that equal to the value in P3? Over here, is the value 44 equal to the value 256? Well, no, 44 is not equal to 256. Now granted, person 1 and person 3 have the exact same contents. The name is the same, and the favorite number is the same. But the memory addresses are different, so this statement would end up being false. This is different from using the dot equals method. What happens here is our P1 calls its dot equals method and then compares P3's properties versus its own. So P1.name is equal to P3.name. Similarly, 0 as a favorite number is also equal to 0. So using the dot equals method, it says the contents of these two objects are the same. But by using double equals, it indicates that these are two different instances of these objects found at this memory location and this memory location. Now let's assign the value P2 to P1. The assignment operator does not create clones of objects. It just assigns whatever is inside of that identifier. So you can see right here, P1 contains the memory address 120. When we set P1 is assigned to P2, what happens is P1 becomes 120. Thus, P1 references this object now. And alongside that, P2 also references the exact same object in memory. It didn't clone it. We just have two different identifiers referring to the same thing. Now this is where things can get very weird. The next statement, what we're doing is we're setting P1.setName to ASDF. Now P1 refers to this name, which basically changes that property to ASDF. So now, if we assign string name and call the accessor from P2, remember, P1 and P2 refer to the exact same object. Even though this was originally constructed as JJ, because we have changed the property from P1, we have thus changed the property in P2. The assignment operator with objects does not create clones. All it does is create multiple references to the same parts in memory. Be very careful about how you use this, but always remember that there is a separation from the reference and the contents of an object. Now you may be wondering, we lost the reference to what originally P1 was. So what happens to this information? As there is no way for us to reference this information anymore, we've lost where the memory address is. Java is a garbage collecting language, which means it finds parts in memory like this and says, well, we don't need that anymore, so let's go ahead and get rid of it. This is how you remove objects from memory. All you do, forget about it. Now, the next principle in object-oriented programming is called inheritance. This establishes a relationship between two classes where the properties and the methods are absorbed from one class into another, and this is very similar to biological inheritance. We use inheritance to create more specific versions of a given class, and this creates an is-a relationship. The reserved word extends is used to establish this kind of relationship, and it is used in the class's definition. Along with that, we use the word super to access methods from a parent class from a child class. Super followed by the parenthesis is a call to the parent's constructor. Super followed by a dot is a call to the parent's method. The syntax, as we can see here, is we first start out with public class, whatever the class's identifier is. Then we use the word extends and the other class. Now you'll notice here that I specifically put a default constructor here. It is a very good idea in Java to go ahead and for every one of the constructors to call the parent's constructor. So this is a call to the other class's default constructor. Now, if we wanted to create a more specific version of a person called an employee, we have employee extends person. This means that the employee has absorbed the attributes, name and favorite number, and now has included a new property called ID. From here, as you can see, in the default constructor, we call the person's default constructor, thus setting its name to none yet and its favorite number to 0. Then we set this .id also equal to 0 here. Now moving down a little bit, here is our equals method for an employee. And it basically follows the same format with one noticeable exception. We call super.equals here. This super calls the person's .equals method, thus passing this employee E to here to check whether or not the name and favorite number match. Now notice, this is of type employee, and this .equals method expects the type person. An employee is a person. This means you can substitute the type employee for a type person. Now, this is a very interesting concept because what this evokes is one thing can become many, and this is the final property of object-oriented programming. Polymorphism. One becomes many. The way to think about polymorphism is think of, can this be implemented in several different ways? One of the cornerstones of polymorphism is a structure called an interface. These are non-constructible types. This means you cannot use the word new in order to create a new instance of an interface. Interfaces do not have instances. There is no functional code inside of an interface, and only it contains method definitions. Interfaces can be thought of as variables for types. So you can have one interface be implemented by a lot of different classes, and the interface's type can be used to contain all of these different classes. Now, just like before, with a class, an interface's identifier has to match the file name, or else it's a syntax error. In order to use interfaces, classes implement that interface. Now, this is unlike inheritance, where you can only inherit from one other class. Classes can implement any number of interfaces. And, most importantly, these interfaces provide rules for how we are creating these classes. In other words, the method definitions inside of an interface have to be implemented inside of the class. If it's not, then the class has a syntax error. In addition to that, you can use inheritance with interfaces, so an interface can extend another interface. So the syntax for this, once again, is you start out with public, but this time interface, and the interface's identifier. From there, the only thing that's in the body of an interface is the method definitions. Now, in order to implement an interface, you start out with the class definition, public class, its identifier, and then the reserved word implements, followed by the interface's identifier. So an example of this is we could create this public interface a drawable object, which only has the method definition draw. Now we can think of like a lot of different drawable objects, and they all draw themselves in different ways. Like for instance, we have this thing called a rectangle, which implements this drawable object. Now even with a rectangle, you could draw that in any number of ways. Are we going to fill the rectangle? Is it just going to be a border? Who knows? So in this case, you can have this class implement this drawable object and then implement this method in any number of ways. So you can have this triangle, you can have an empty triangle, you can have a filled triangle, but either way, they're all this drawable object which we know has the method draw. We've gone through a lot more information today in order to review everything there is to know about programming before we get to those data structures. The main idea is this. Think of methods as a form of organizing functional code into verbs. They are your actions. Methods can then be grouped together along with properties into another structure called a class, and instances of classes can be considered nouns. Verbs are your method, classes are your nouns. And with all that being said, I'll see you next time.